0 to 2 pi. Your final answer is like this: I is equal to Im square by 2, or you can rewrite like this: I is equal to Im by root 2, which is equal to 0.707 Im. So this will give you the RMS value of current for a alternating quantity when you are considering the full wave configuration. Now same thing you can derive for a half wave configuration. So for half wave we are consider that we are having a half wave configuration. So your waveform is conducting only in a positive half cycle, and for negative half cycle it will not conduct, as shown in figure. The full line indicate that it is conducted in positive half cycle, and dotted line indicate that it will not conduct in a negative half cycle. So a half wave rectified AC is one in which the current flows only during one half of a cycle, as shown in figure. So same equation you can apply for a half wave rectifier. Only difference is that you have to change the limit of integration, because in half wave you got the output up to 0 to pi only. In pi to 2 pi your output is 0. So equation is same: I/RMS is equal to under root of 1 upon 2 pi. 2 pi is our time period. Integration 0 to pi, because it is a half wave rectifier. I square, because we are considering the amount of heat, and d theta. So I is equal to Im sin theta. So it is like this: under root of 1 upon 2 pi integration 0 to pi Im square sin square theta d theta. Again sin square theta is equal to 1 minus cos 2 theta, and Im is remains constant throughout the cycle. So it is like this: Im square upon 4 pi integration 0 to pi 1 minus cos 2 theta d theta. Now simplify this equation. So after simplifying you got like this: Im square upon 4 pi. Here it is theta minus sin 2 theta by 2, limit is 0 to pi. So your simplification is like this: put the limit between 0 to pi, so your answer is pi. So Im square divided by 4 pi into pi, so it is equal to Im by 2. So it will give you the answer of I/RMS for alternating quantity, which is equal to 0.5 Im for a half wave configuration. So for full wave got the answer which is equal to 0.707 Im, and for half wave it is 0.5 Im. So these are the values of I/RMS for alternating quantity when you are considering half wave and full wave configurations. Now we are switch over to next topic, which is average value. Now average value is given by the steady or direct current which, when flowing through a given circuit for a given time, transfers same amount of charge as it transfer by AC when it flows through the same circuit for the same time. Now when we are considering about RMS value, we are concentrate on the amount of heat produced by alternating quantity, but when you are considering about average value, you have to concentrate about amount of charge transfer by the alternating quantity. This is the main difference between RMS value and average value. In RMS you have to consider about amount of heat, in average you have to consider about amount of charge transfer by alternating quantity. So in RMS value heat is equal to I square RT, so you have to concentrate on I square. But when you are consider about average value, it is the amount of charge which is directly proportional to current, so it is just a current. In RMS it is I square, in average it is I. Next is determination of average value. Same way two methods are available. First one is the mid-ordinate method and second one is the analytical method. Mid-ordinate method is same as we are discussing RMS value. So this method is again applicable for both sinusoidal and non-sinusoidal waveform, and average value of AC is given by the arithmetic mean of the ordinates of that quantity at equal intervals over a half cycle. Now why this is for half cycle? Reason is that when you are considering the full wave configuration, then what happen? For full wave it has some positive values, and for negative half cycle it has some negative values. If you are find the average for a whole cycle, then the average of positive having suppose +5 and average of negative suppose it is -5, and you are adding this 2, so your answer is equal to 0. So whenever you are considering the full wave configuration, always consider a half cycle only, because if you are consider a full cycle, your answer for average is always 0. So for full wave we are considering only the half cycle to find the average value. So this is the mid-ordinate method for non-sinusoidal waveform. Same way, divide your waveform into number of parts. Here it is divided into 10 number of parts, and find the instantaneous value of voltage for each part for a n number of part. Same way for positive you can apply also for a negative half cycle. So this is the equation for V average, which is equal to V1 plus V2 up to Vn divided by number of parts. Same method you can applicable for sinusoidal waveform. Again, divide your waveform into number of parts and find the instantaneous value of voltages for individual part, and then find the average for a whole wave. So V average is equal to sum of all the mid ordinates upon number of mid ordinates. For example, in this particular figure we are considering 12 number of parts. So it is addition of V1 plus V2 up to V12, and number of mid ordinates are 12, so divided by 12 it will give you the average value. This is the mid ordinate method for sinusoidal waveform. Now analytical method. To find the average value using analytical method, you have to find the area under the cycle as shown in figure. As I discussed earlier, we are considering only the positive half cycle, so we are concentrate on positive half cycle only. You have to find the area under this particular cycle, and after that you can find the average value for a particular quantity. So area under the positive half cycle is equal to 0 to pi Vp sin omega t. This is the equation for a instantaneous induced EMF or instantaneous induced voltage. Now arithmetic mean found over one cycle of full wave is 0, that I explained you earlier. So average value found over a half cycle only. Now analytical method I can explain by OHP. Same way in RMS value. In average value also two configurations you have to consider, full wave configurations and half wave configurations. So for analytical method, first of all we are considering the full wave configuration, means you have a output in positive half cycle as well as in negative half cycle. So equation of alternating voltage V is equal to Vm sin theta, and you have to find the average. As we are discussed earlier, instead of whole cycle we are considering only the half cycle. So V average is equal to 1 upon pi integration 0 to pi V d theta. Now equation of V, instantaneous induced EMF V, is equal to Vm sin theta. So your equation is like this: Vm upon pi integration 0 to pi sin theta d theta. Again Vm is the constant value, so it is Vm upon pi, kept it as a constant, and integration of sin theta is minus cos theta. Limit is 0 to pi. So your final answer is 2 Vm upon pi, or it is equal to 0.637 Vm. So this is the average value of voltage for a full wave configurations, which is equal to 0.637 Vm. Same way you can derive the equation for average value for a half wave configuration by analytical method. Okay, as we discussed earlier, for half wave we got output for a positive half cycle only, and for negative the value is equal to 0. So you got output between 0 to pi, and for pi to 2 pi your answer is equal to 0. So as shown in figure, it flows only over a half cycle. but it average over the entire cycle. Reason is that suppose you are find the average for a player of a cricket. He plays 5 matches. Between from this 5 matches, in 2 matches he scores 0 run. Then if you have to find the average, then it is equal to 1 plus 2 plus 3 plus 0 plus 0 divided by 5. Because the number of matches played by this player is 5, you have to consider the number of matches is equal to 5. Although in 2 matches he score a 0 value, same funda you can apply for a half wave rectifier. In the half wave rectifier, between 0 to pi you have some values, and pi to 2 pi you have 0 values. So whenever you find the average, you have to consider a whole cycle. In full wave, what happen? The positive half and negative half are identical, so effect of these two is cancel out. But in half wave, positive half having some values, negative half having a 0 value. So for half wave configuration, you have to consider the time period from 0 to 2 pi. Pi to 2 pi it has a 0 value, but you have to consider effect from 0 to 2 pi because it is your whole cycle. So to find the I average, you have to use this equation. It is 1 upon 2 pi. In full wave we are using 1 upon pi because we get an answer for positive and negative both the half cycle. So we are considering only positive half cycle for a full wave, but in half wave you have to consider a whole cycle. So it is equal to 1 upon 2 pi integration 0 to pi again I d theta. So I is the instantaneous value of current, so which is equal to Im sin theta. So 1 upon 2 pi integration 0 to pi Im sin theta d theta. Again Im is the constant value, so it is Im by 2 pi. Integration of sin theta is minus cos theta, so here it is minus cos theta. Put the limit from 0 to pi, so our answer is equal to Im upon pi. So this is the average value of current for a half wave configurations. So in full wave it is 2 Im upon pi, for half wave it is Im upon pi. So always remember one thing, whenever you are considering full wave configuration, consider only half cycle. When you are consider half wave configuration, you have to consider the entire cycle. So it is 1 upon 2 pi. For full wave it is 1 upon pi, for half wave it is 1 upon 2 pi. Clear? Now as we discussed earlier, for half wave rectifier AC flows only over a half cycle, so average value over complete cycle will not be equal to 0. An analytical method for half wave is already discussed. Now form factor. Form factor is defined as the ratio of the RMS value to the average value of an alternating quantity. Now as we are discussed, RMS value is nothing but the amount of heat produced by alternating quantity, and average value is nothing but the amount of charge transferred by alternating quantity. Ratio of these two will give you the form factor. This is the equation for form factor, which is equal to RMS value upon average value, which is RMS value is 0.707 Vm and average value is 0.637 Vm. This is for a full wave. Same way you can apply for a half wave configuration also. Now peak factor. Peak factor is defined as the ratio of peak value to the RMS value of an alternating quantity. Peak value is the maximum value attained by alternating quantity, and RMS value again it is the amount of heat produced by alternating quantity. So ratio of these two will give you the peak factor. This is the equation for a peak factor. Peak factor is also known as a crest factor, which is equal to peak value divided by RMS value. So Vm upon 0.707 Vm. Now this is one example which will shows the clarity about peak factor and form factor. So a sinusoidal alternating current of 6 ampere is flowing through a resistance of 40 ohm. So you have to calculate the average voltage and the peak voltage of the supply. Okay, so first of all, RMS voltage value is calculated as VRMS is equal to amount of current which is given and resistance of the circuit, which is also given. Current is 6 ampere and resistance is 40 ohm. So your voltage is 240 volt. Now the average voltage is calculated as by using the form factor, which is equal to V_RMS upon V average. So V_RMS is already known. So V average is equal to V_RMS upon form factor. So V_RMS is 240 and form factor is 1.11, which is equal to 216.2 volts. Now peak voltage. Peak voltage is equal to RMS value into 1.414. 1.414 is nothing but the peak factor. So value of peak factor and the form factor is always remains constant. So whenever in exam these values are not specified, you can consider it as a 1.4 and 1.11 for all the examples. So your peak voltage is equal to 240 into 1.414. This is your peak factor. So your answer is equal to 339.4 volts. Now other examples that I will explain you. An alternating current of frequency 50 Hz has a peak value of 100 ampere. Okay, peak value of current is given. So you have to write down the equation for its instantaneous value and also find the time taken to reach 80 ampere for the first time. So in this example you have to find the time taken to reach up to 80 ampere for the first time and instantaneous value of the current. So given data is frequency is given, it is 50 Hz, maximum current is given, which is 100 ampere, and instantaneous value of current I is also given, it is 80 ampere. First of all you have to find the instantaneous value of the current I. Equation of I is equal to Im sin omega t and omega is equal to 2 pi f. So frequency is 50 Hz, so your omega is equal to 2 into 3.14 into 50 Hz frequency. So our answer is 314. Again unit of the omega is radian per second. So you can use this value in the above equation. So I is equal to 100 sin omega is equal to 314. So 100 sin 314 into t. Now 80 is the instantaneous value of current which is given in the data. So 80